My computer's, they put it in.
Welcome back to ECE 442-542. We are one lecture after exam number 1. I do have the exams with me. Don't let me forget to hand those or return those back, and we'll talk more about that at the end. Homework number 3 is not due this Friday. This is a Monday, is that correct? Trying to remember what day we are on. And homework 3 will be doing or dealing with inverse Z transforms and how you then use the region of convergence to tell you what you're obtaining as an answer. That's why we're interested in the region of convergence. Today we will actually start, and as a reminder, just for your planning purposes, exam number 2 is March 11th. That's a couple of Wednesdays from now, not 2, but a little bit more than that. Today we will start, as I said, with an in-class activity. I will see where we're at relative to inverse Z transform, and we haven't talked about that really in the sense of taking an expression and finding the inverse Z transform, but I want to see where we can get to based on what you already know or don't know from previous classes. Then we will spend some time, quite a bit of time, talking about the region of convergence, and I want you to get comfortable with the patterns relative or with respect to the poles. There's really only 3 patterns. We have this inner circle that's shaded. We have the entire Z-plane with the center cut out, and then we have this donut shape or annular region. Those are the 3 patterns, and those are all going to be relative to our poles in the Z-plane. And what do we know about the poles in the Z-plane relative to the region of convergence? Where do they live? Where do the poles live relative to the region of convergence in general? What's a general statement that you can make relative to the poles where they are living in the Z-plane relative to the region of convergence? And this is all very semantic in terms of, I hope that I explain it well, but your poles cannot be inside living on the region of convergence, no matter which pattern you have for your region of convergence. We will talk about causal, anti-causal, and two-sided, and that's not necessarily connected, or these are independent of a bounded or unbounded response. So you have basically 4 different patterns that you could look at. You could say, I have I have a causal bounded, I have a causal unbounded. I have an anti-causal bounded, I have an anti-causal unbounded. And then you can have two-sided that fall into those same categories. Bounded and unbounded, two-sided. And then we'll talk about, well, what's all this inside the unit circle idea relative to systems and pole locations? Why is that maybe seeming to be different from all of these different patterns that we're having relative to bounded signals? But I want you to start getting comfortable with the idea of having signals and systems and the transforms of those, or these expressions, these transformed expressions. You might have a system transformed, or you might have a signal. And that means you might be interpreting these ideas. We will be dealing with causal, anti-causal, and two-sided relative to signals. And really, we're only going to worry about having a causal system since this is a controls class. It might be a little bit odd if we had a system shaking before we kicked it. That would be difficult to control. That's why we deal with causal systems. That means when we kick it, it then shakes. It doesn't shake before it's kicked. Okay? And that's why we can maybe have this restriction or this concept of poles inside the unit circle governing system stability. And hopefully that will be clear after we talk about or talk more about the region of convergence. And then we'll get into this new idea of introducing discrete equivalence, which we've already started on. We designed a low-pass filter, a digital low-pass filter based on an analog low-pass filter. We want to get comfortable doing that. If I give you a filter, analog, can you generate or create a digital filter? If I give you a system, can you give me let's say I give you a S-domain or a Laplace transform system representation, can you then provide me with a system that's for a discrete time setting or a Z-transform? And now we'll start talking about zero-order hold equivalence. You've probably already read that when you were getting anxious studying for exam number 1, when you kept seeing generate or provide the zero-order hold equivalent of this system. That's where we're headed with discrete equivalence. And we have more than just zero-order hold equivalence that we can deal with. I want you now, in-class activity, to spend a couple of minutes telling me what little f of n is if you are given capital F of z and this rock. Oh, I'm sorry, the gym show ended. Region of convergence. I want you to now start, begin, go, find little f of n given capital F of z. Do we need more time? Show of hands. Who needs more time? No one's even looking up. I can't tell if you need more time, if you're writing a letter to your mother, or what's going on. Actually, that's what somebody said. If they're having trouble learning how to, or getting a story written, it was a fiction writer, I think, he writes a letter to his mother. And maybe it's about this bear, and he's having trouble with figuring out how he's going to get started writing a story about a bear, but it breaks the ice if he can write that letter to his mother telling her all about this bear and saying, oh, this is really struggling with this. So he just erases all the pieces about his mother, and then he has a start on his story. I thought that was kind of clever. So if you're stuck with writing your capstone project report, you can just tell your mentor, oh, I started writing a letter to my mother. A bear. Well, maybe not about a bear, but your project. And then you're on your way. Now, with respect to this, I have no idea where that came from, but I guess it was because nobody was looking up when I said, do you need more time? That's where that came from. Was anyone looking for extra credit? And if so, how did you start? What was the approach that you used for finding little f of n? Did you start relating this? Well, answer. I need to be running up the stairs with a microphone, don't I? Yes, sir? Partial fraction expansion. Did people do that based on what they've done in Laplace? With Laplace, when you had these different factors in the denominator, each of those factors you said, oh, I know what the inverse of that is if I just pull it apart, if I partial fraction expand. And if you partial fraction expand this, what do? Do you say, so now we're saying, okay, one strategy is partial fraction expansion. Did you partial fraction expansion f of z? Better put my eyes back on. If you did, then you have something like a over z minus 1/2, plus, let me say a1 plus a2 over z minus 3/4. Which, if you now found a1 and a2, can you find this in your table of transforms? Or in your table of transforms, if you remember that, if you have it memorized from exam number 1, you may have had something like z over z minus r. And there's no z. Don't answer that. You don't need to be zing right now just yet. We're only 10 minutes into class. So, but you might be missing a z if you just did a partial fraction expansion of capital F of z. And so it's not a direct identification of this transform pair easily from the transform table. And the strategy to remedy that is to say, well, I can force a z in the numerator after I've partial fraction expanded if I start with f of z over z. If I now take and divide f of z by z, I now have this 1 over z minus whatever it was, 1/2 times z minus 3/4. Now I have, let me say, an a1 bar and an a2 bar, which I can compute using the same strategies that I've always used to find these partial fraction expansion coefficients. Find a1 bar, seeing that it is associated with the denominator factor z minus 1/2, I can multiply all sides or all terms by z minus 1/2, and I can say a1 bar is now 1 over z minus 3/4 evaluated at z equal to 1/2. Evaluating it at z equal to 1/2 causes that A2 bar piece to go away, because that now becomes 0, and all you're left with is A1 bar equaling this expression. And that's minus 1/4 in the denominator, and that then gives us a minus 4 for A1 bar. Is that correct? Did I do the algebra right? If I didn't, I'll just blame it on my glasses. Didn't have them on, or I didn't have them off. Somebody was writing on their exam when I was grading it. No, I'm teasing. Blame it on my glasses. No. A2 can be found the same way. A sub 2 bar. We multiply through by z minus 3/4. Us with, on the left-hand side of the red expression, 1 over z minus 1/2. We evaluate that. 3/4. And now we get A2 bar is 4, so that f of z over z would be this minus 4 over z minus 1/2 and plus 4z minus 3/4, but we've taken the z from underneath f of z now and put it back into the proper location by multiplying all terms by z, and now we can identify these two terms on the right-hand side with where they belong, or the pair that we have in the z transform table, which now says that f of n is minus 4 1/2 to the n plus 4 3/4 to the n. What values of n do I have? And how do I know? I use the region of convergence to tell me which n's I can evaluate, or that are valid for this expression of little f of n. My region of convergence relative to these poles at 1/2 and 3/4 the region of convergence was outside of, or exterior to, all of the poles. Now, how does that give me the values for little n when this expression is valid for little f of n? That we can deduce. If we don't have it memorized, we can go back and we can say, okay, capital F of z, we were told it existed, and by definition, that's this sum from n equal minus infinity to infinity of little f of n, z to the minus n. Maybe it's not clear from that compact form with this summation symbol what that looks like, but we can start building this up. We can say f of minus 2, z to the minus minus 2, plus f of minus 1, z to the minus minus 1, plus f of 0, z to the 0, plus f of 1, z to the minus 1, plus f of 2. That's now our more detailed representation of capital F of z. And this right-hand side is supposed to produce a bounded number, a finite sum, for all of the z values in the region of convergence. That's what the region of convergence means. And now we can pick a convenient value of z to see how we can interpret which of these pieces of all of these terms must be present or not present. If we look at the region of convergence again, what might be a convenient value to select for z to plug it back into those terms to see which of these terms need to be there or not there in this case? And it may not be on my screen. Hint, hint. You may want to try to find a really big z, a z that's going off to infinity. If z is going off to infinity in this expansion, what does that tell you about some of those terms? If this capital F of z needs to converge. Do you see what I'm trying to get you to see? If I plugged in a z going to infinity with this f of minus 2 z squared as z is going off to infinity, what's that telling you about f of minus 2? Pardon? You want this sum to be bounded, and if f of minus 2 is non-zero, you've got problems, don't you? What about f of minus 1? F of minus 3? They all have positive exponents with z, and if I let z be going off to infinity, those are going to produce an infinite sum, and that's not going to be a bounded number or value for capital F of z for all these z's in the region of convergence. What I hope this is showing is that the z's, or I'm sorry, the terms in this expansion that are okay are the ones with the z in the denominator, the 1 over z, the 1 over z squared. You can have a big z in those terms. Those are going to be okay. The ones with z in the numerator are going to cause you difficulties. What I'm trying to get us to see then is that from the region of convergence, which this region of convergence includes unbounded values of this complex variable z, i.e., or that is z going off to infinity, that's forcing these time values of little f of n, when n has a negative time index, to be 0. And now if you wanted to, what does this, all of your f of n's for negative indices are 0, and the f of n's for positive or non-negative n's are non-zero, what kind of a sequence is that? Right-sided or left-sided? Or what I'm going to be calling right-sided, I'll be calling causal, and left-sided I will be calling anti-causal. What does this correspond to if, in fact, f of n is not equal to 0 for n non-negative? Causal or anti-causal? And the connection that you can maybe make now is that this unbounded region of convergence is connected to this causal behavior or causal sequence of values. And that allows us now to go back to our answer and insert, this is true for non-negative n's based on our region of convergence. Who went out and bought a calculator just for this class? That's good. Didn't see a show of hands, but have you purchased a calculator for other classes thinking it might save you time? And if you did, wow, he came in and messed me all up. But if you have a TI calculator, you can do this partial fraction expansion pretty quickly. You simply go into, either you can type it if you're quick with your typing, or you can go in, I've already found it. Imagine that. But if it was maybe on the A's, you could just say, well, I need to go to the back side of the E's, so I'll go to the F, then I'll say expand, and I could say 1 divided by, and give me, whoops, what did I just do? Oh, keyboard's not behaving, is it? Yeah, because I've got it. Ugh. Should have. I could type with the mouse, but then I would really start getting frustrated. But, pardon? It was just numlock. So I figured out that that was okay. And that's now what we have with a fairly quick couple of entries with the calculator, and we now have our partial fraction expansion. And I hope that's consistent with what we just computed by hand. That will potentially save you time. I'm hoping that it doesn't cause you to not, or to lose sight of what you're actually doing, that you can actually do this by hand. This is just a saving tool for you, and you can tell your mom or your dad, oh, thanks for that calculator. Or if you bought it yourself, you're more appreciative of what you just bought, right? Questions on that example and where we, just given this capital F of Z, could you immediately, based on your understanding from exam number 1, could you have immediately written down the structure, the generic structure of your answer? What influences the structure? This would be like an initial condition response, essentially, in a system, or if this is a signal, now those poles are influencing your structure. You now have 1/4 to the n and 1/2, or 3/4 to 1/2 to the n and 3/4 to the n. You know that that's going to be a part of your answer. And you know exactly what those coefficients are from your partial fraction expansion. Let's look at another example. That was a region of convergence that was unbounded. It had the center cut out, and it included all the other points beyond that center that was cut out. What about annular region of convergence? And we could, let's just say that we have a pole at 1/2 and another pole at 3. I shouldn't have put that 3 so far out, but there's one radial distance, and there's another, and we're saying now that our region of convergence does not contain those poles. Those poles bound the region of convergence. The pole at 3 is just beyond the region of convergence, and the pole at 1/2 is just inside the region of convergence. There is our donut shape or annular region for this problem, and in particular, we could produce that if we had a time sequence, little f of n, made up of two pieces. F sub 1 of n, let's say, is 2, 3 to the n for n less than 0, and f sub 2 of n is, let's say, 4, 1/2 to the n for n greater than or equal to 0. Where we could say, oh, if we've defined f1 of n and f2 of n, then we could write f of n, knowing when these particular expressions are valid with their time index. We would then have little f of n is f sub 1 of n plus f sub 2 of n, knowing f sub 2 is non-negative indices and f sub 1 is negative indices. We can now find capital F of z by looking at these two parts. What was f sub 1? That was the negative index, so let's look at what we have there. F sub 1 of z is now this sum from n equal minus infinity to minus 1, f sub 1 of n, z to the minus n. We can replace little f sub 1 of n with what expression we said it was, 2 times 3 to the n, z to the minus n. The 2 impacts all of the terms in that sum. We can factor that outside of the sum. And we can actually combine those terms that have an exponent of n by putting the z downstairs, since it had a negative exponent and the 3 had a positive exponent. We now have 3 over z to the n. Do we remember what that would look like in terms of this closed form expression? Or not? And how would you do that? Do you remember how you might find an expression for capital F sub 1 of z? If you didn't worry so much about the 2 and just looked at the infinite sum, you could say something like, well, I have an s equaling these pieces, which is 3 over z to the minus 1 plus 3 over z to the minus 2 going backwards in terms of the time indexes. Do you see where that's coming from? I'm now saying that I'm interested in calling that expression S. And now we could do our little trick that we've learned how to do. We now know that those individual terms in the summation differ by a 3 over z to the minus 1. we can get rid of or produce something a little bit different on the right-hand side, but you still leave the tail by multiplying S by 3 over Z. And that now gives us 1 plus the tail that I was talking about. Do we know when that sum is going to converge? We've assumed it did if I set it equal to capital S. When will capital S be a valid number? On what condition on that term 3 over Z? We need 3 over Z to be bigger than 1 now since we're raising it to a negative exponent. Is that clear? We want that basically bigger than 1 since that's all in the denominator. And then it would be well behaved because we'll now have something that we will square, cube, etc. This is now going to be valid as long as 3 over Z is bigger than 1. And from this, we can subtract the bottom from the top, and we have 1 minus 3 over ZS is minus 1, which allows us to say that S is this minus 1 over 1 minus 3 over Z, or we now have minus Z, Z minus 3. And that was scaled by 2, so that now we have 2 minus Z over Z minus 3. And that was true as long as 3 over Z was bigger than 1. Or what does that look like if we sketched that region in the complex S-plane? Complex Z-plane. Got too many Z's now floating around. Z, the absolute value of Z, needs to be less than 3. Region of convergence. And if we went back to this expression for our sum, which of these terms now, if we pick a convenient value for Z in this expansion that's supposed to be bounded, which value of Z would we pick in this region of convergence that might allow us to say, oh, now we know what side, whether we have a causal or anti-causal, or whether n is non-negative or negative in terms of the indices. We go to the extreme again, don't we? If we went back to this, now if we have 1 over Z and we're dividing by 0, or if we let Z be right at the origin, that's forcing these time indices that have non-negative or positive indexes to be 0. Meaning when we have this particular region of convergence, that's implying this time index where our waveform is valid, and that's what we were given to begin with anyway. We said that little f of 1 was valid for negative values of n. And we now hopefully understand where that's coming from. What about f sub 2 of n? What does it look like? Capital F sub 2 of z is this 4 times this sum from 1/2 to the n, z to the minus n equals 0 to infinity. And when is that going to produce a valid sum? What condition on the argument are we looking for? Especially if we slide that z maybe downstairs and we have a positive exponent n. Now we have something raised to the n. What do we need that something to be in order for that infinite sum to converge? Is that thought process clear? Now we want 1 over 2z less than 1, or we now have z outside of 1/2 in value. And knowing the relationship between that time sequence and its z transform, we can write down that f sub 2 of z is 4 times z over z minus 1/2, when in fact we have our region of convergence for f sub 2 of z outside of that pole at 1/2. And to find the region of convergence for f of z, capital F of z, we can just look at the region of convergence for the first function, capital F sub 1 of z, and intersect that with the region of convergence for f sub 2 of z. Intersect this unbounded region of convergence in 2 with this region number 1, and what do we end up with as an intersection? There's our annular region. And those values of z are when both of those transforms exist, values. We now have something beyond 1/2 and interior to 3. There's the intersection. And how is that relative to the unit circle? Or if we draw the unit circle on that z-plane diagram, is the unit circle living, or does it belong on top of or inside the or I don't know the semantics maybe to say that, but now do you see that the unit circle is contained in the region of convergence? What does that mean? Does that tell us anything about the behavior of f of n? Is f of n bounded? And you could even go back to the beginning expressions for f and say for those particular values, what's actually happening to the time sequence little f of n. Do you see what's happening for the anti-causal piece? 1/3, 1/9, etc. That's decaying. And what's happening to the right-sided part, or the causal part? 1/2, 1/4, being scaled by the appropriate value, but that's also bounded. And we knew from this picture of the region of convergence relative to the unit circle that little f of n is in fact bounded. And f of n was two-sided. What if I gave you another region of convergence for those same two poles? Suppose that I now gave you the following. Here is 1/2. Here is 3. This is the z-plane. And now suppose that I say the region of convergence is outside of both poles. So this is another region of convergence for the same poles. What do you know about the structure of this time domain response, just with this pattern of poles? Do you know the structure? And what is that structure based on? Those little X's are very powerful, aren't they? You now know that the two pieces that make up your response, if we called that W of n, we have something, let's say alpha 1 bar, 1/2 to the n plus alpha 2 bar, 3 to the n. Do we know anything about when n is valid based on this region of convergence? This region of convergence is saying that we have z bigger than 3. That's our region of convergence. Do you remember going back to that series or that summation expression with these big Z's, what that implies on the time index that this is true? And is that time index true for both pieces, the 1/2 to the n and the 3 to the n? Where is that region of convergence relative to both poles? for both modes. Does anybody have a coin? How many options do we have for little n? Heads and tails, right? How many ways can the instructor fall down the steps? More than sides of a coin, I'm afraid, unfortunately. But if you had a coin, you'd have a 50-50 chance of getting that right as far as what ends you use. There's just two sides to that coin and two sides to n, little n. Which side are you on? Call it in the air. Is it left-sided, anti-causal, or right-sided based on, now pick a convenient value for z. Which z is convenient in this region of convergence pattern? Z goes big, doesn't it? So you can have a big Z. You plug a big Z into this expression, and what terms need to not be there? The F's with what ends? Negative ends or positive ends should not belong. Now I feel like I'm in Sesame Street. One of these ends does not belong. N positive or N negative? N negative does not belong, does it? If we had a big Z, then those are going to go unbounded, and we can't have that. This picture for the region of convergence immediately implies that n is bigger than 0, non-negative, which now says that this is our structure and the time in which that's true. Is that a bounded sequence or unbounded? Is it causal or anti-causal first? It's causal, isn't it? It's happening after 0, times 0. That's what we're calling causal. Is this sequence bounded or unbounded? Three squared, 3 cubed, 3 to the 4th. What's that guy doing? He's getting very, very big, isn't he? So this is unbounded, even though it's causal. So those are not necessarily connected. That's what I'm wanting to drive home. The causality was determined by the pattern of the region of convergence. The bounded nature is based on where those poles are. If that pole at 3 was allowed to get smaller and go inside the unit circle, then you would have a bounded causal behavior. Let's start looking at some of these observations that I'm hoping we're starting to acquire. Based on, did I hear a question? Can't see it, but I might hear it. Okay. Region of convergence, let's say observations. Suppose we start with maybe the one that's a little more interesting. As soon as we say an annular region, what do you know about the sidedness of your time sequence? Do you know anything? All right, let's see what we know. I heard two-sided and I heard right. Did I hear a left? I feel like I'm an auctioneer now. But let's say that we have poles at these four locations. This is, let's say, pole 1, pole 2, pole 3, and pole 4. Those are not zeros. Those are just labels on my poles, even though I've enclosed them in circles. And let's say that our region of convergence is annular and the annular nature or pattern is defined by these bounds from pole 1 and pole 3. Do you see that you could create a lot of different annular patterns from these four poles, but you're still going to have an annular pattern? You could have that donut between 3 and 4. You could have the donut between 1 and 2. But you can't have poles inside the region of convergence. Is that clear? Now, let's see what we can do with this particular picture. Let's see how we can associate these poles with the appropriate time behavior or indexes. Associate the poles. Hopefully this writing will be clear. Larger than the annular region. And that just corresponds to poles 1 and 2. Is that clear what I'm trying to say? Associate the poles larger than the annular region, or those poles that are beyond the annular region. Now pull out your coin, and which one is it? Heads or tails? Right or left? What's the little n that this corresponds to for those poles, 1 and 2, with the annular region now inside those poles? So take it to the extreme and just say 1 and 2 are all I have. I don't have 3 and 4 right now, which you now have this region of convergence that's interior to poles 1 and 2. What time, right or left, does that correspond to? Left. Negative n's, doesn't it? So this is with n less than 0. You could say, another way of saying that is you now have region of convergence interior to poles 1 and 2. And depending on where 1 and 2 are located, maybe they're at 10 and 20, then you have 10 to the n and 20 to the n. And that n is now negative. That's what this picture tells you. We haven't yet labeled where 1, 2, 3, and 4 are on that diagram, but just knowing the relative location of 1 and 2 relative to the region of convergence tells us n less than 0. Likewise, and the poles smaller than the annular region, which are poles 3 and 4. Now, since we've already flipped the coin and we won, and we elected to go negative, didn't we? Yes, before. Now, the second half, were positive for those poles 3 and 4, or we could say that the region of convergence is exterior to poles 3 and 4. No matter where 3 and 4 are, if 3 and 4 are at 1 and 1.5, then we have 1 to the n and 1.5 to the n. Would those be bounded or unbounded? Relative to n being positive. If 3 and 4 are at, maybe I should call them, let's say 4 is at 1 1/4 and 3 is at 1.5. Do you see what's happening in the time response behavior? Are those growing or collapsing as n gets bigger? Those poles, the modes due to those poles. They're growing. And where's the unit circle relative to the unit to that region of convergence? If 4 is at 1 1/4, the unit circle is not contained in the region of convergence, is it? So you do not have a bounded response. If 3 and 1 were positioned to where the unit circle was between them, then you would have a bounded response for those 4 poles. Let's see if we can summarize that. Let's say B, observation. If the region of convergence, and we're defining that region of convergence to make that sum bounded. So these values of z are defined such that that infinite sum is well behaved, or it gives you a bounded answer. So if somebody says, here's your region of convergence, you know that all points z in that region of convergence make that sum converge. If the region of convergence contains z's that have a magnitude of 1, and what do we call that? That's just a mathematical way of labeling the unit circle, isn't it? The magnitude of z equal to 1. That's just the unit circle. If the region of convergence contains the unit circle, what do we know about the time sequence? Then the time domain sequence, one-sided or two-sided, it doesn't matter, is bounded if we're dealing with a signal, and if it was a system, then we would say that that system is stable. Which we are really saying, or another way of thinking of that, or that is, if we were looking at this sum, we could, if the region of convergence contains the unit circle, then we know that z equal to 1 is a value of z that's on the unit circle, so we can replace z with 1. And now we know that even though this is f of minus 3 plus f of minus 2, because the z was in the region of convergence, that means by definition that this is bounded. All of these, since they're scaled by 1, those are bounded. And we now can picture, it doesn't have to be this nice, but because we could have some alternating signs, and these don't have to be at the same rate. They should be spaced the same, which my picture might not produce that. But this is now f of n if our region of convergence contains the unit circle. Because the region of convergence, by definition, are those values of z that cause that f of z to be well behaved. Let's look at some different region of convergence possibilities. Suppose that I now have a pole at 1/2, a pole at 3, and a pole at 4. And now I'm going to try to shade these with different colors. Suppose one choice for the region of convergence. Well, this is going to get kind of busy. That's region of convergence number 1. Region of convergence number 2, let me say that that's the red region of convergence. That's supposed to be symmetric. Bagel didn't turn out very symmetric, did it? But this is now region of convergence number 2, and suppose that another symmetric region of convergence is beyond all of the poles. Do you see how many different types of problems I could have on exam number 2? I could just go crazy with coloring. You may want to go out and buy the 48 box of colors or crayons. Your mother's going to say, I thought you outgrew that. No, my instructor said I needed to get the 64 pack or whatever it is. They've probably got colors today that I didn't even have growing up, right? Chartreuse or something. Who knows? All right, let's look at this. Region of convergence number 1. What do we know about region of convergence number 1 relative to, I have 3 poles, 1/2, 3, and 4. I could say that that region of convergence is interior to all 3 poles, or all 3 poles are exterior to the region of convergence. Region of convergence is interior to all the poles. Does that tell me anything about this side of the coin? And here our coin is causal or anti-causal, isn't it? All terms in the time domain structure are on which side of the coin? Right, left, non-causal, causal. Now the convenient value of z is the origin, isn't it? Z equals 0. You plug that into that infinite sum and you go, oh, now I know which one it is. Now I need these to be non-causal. All of my exponents, or structure of the waveform, if you needed to write it down, let's say f sub 1 of n is alpha 1, 1/2 to the n plus alpha 2, 3 to the n plus alpha 3, 4 to the n. This is true for n negative. We could write it as 1. We didn't have to break it up. It's not two-sided. It's one-sided, and it's left-sided. It's non-causal. These are negative indices. Are those three pieces well behaved? And just look at them individually. 3 to the minus 1, 3 to the minus 2. That seems okay. 4 seems okay. 1/2 to the minus 1, minus 2. Uh-oh, that 1/2 is popping up. This now produces an unbounded response in the time domain, but we could have inferred that from what on our region of convergence and what other piece in the z-plane? The unit circle. If we sketch the unit circle relative to the blue circle, where's that unit circle? It's not in the blue, is it? So we could have inferred from that region of convergence immediately that we were going to have an unbounded does not contain the unit circle. And because of this not, we had this unbounded time response. What about region of convergence number 2? This one's a little bit more interesting, isn't it? What pattern does it fall into? The red pattern. I know it's hard to tell from my sketch, but hopefully your sketch is better. I think I referred to that as a bagel, didn't I? Even though it was lopsided. It's annular. What do we know about an annular region of convergence and its time sequence? We have two sides, don't we? And which of these modes appear in what side or are corresponding to the appropriate side? How do we decide on the side? Pardon? That's fine. I want you to be talking to me. Whether I can hear you or not is another story. Wow, that looks kind of nice. It's big, isn't it? It's kind of small when I'm up front. What do we know about this annular region? What ends are associated with 1/2? Where's the region of convergence relative to 1/2? It's outside, isn't it? And what do we know about the region of convergence when it's outside of a pole? What ends are associated with that structure or that mode? Causal. The others are, or the region of convergence is interior to 3 and 4. Those are the negative indices. So with region of convergence number 2, just saying this just the opposite of the order that I just said, but it is interior to poles z equal 3 and z equal 4, and exterior what do we know about the bounded behavior of this time sequence? And how could you tell that immediately? You could sketch the unit circle and say, oh, that unit circle is actually inside that region of convergence. Here you have 1/2 to the n, where n is positive. That's collapsing. You have 3 and 4 with n that are negative. Those are collapsing. You have a bounded two-sided sequence, and you can tell that from the region of convergence and these relative pole locations. I may let you figure out what the waveform structure is for that and number 3, because we are out of time.